This video is on the extraction of metals. So here are our aims for this video. So we need to know the reducing agents, the reaction equations and associated considerations in the extraction of iron, copper, manganese, tungsten, titanium and aluminium from their ores. Now that sounds like quite a lot of stuff to remember and learn, but actually there's quite a few similarities between a lot of them, and I'll discuss those when we go through them. And to know how sulfide ores are converted into oxide ores and the environmental consequence of this process. So when we extract metals from their ores, we are essentially reducing them, because in their ores they're going to be have a positive oxidation state, and as an elemental metal they're going to have an oxidation state of 0, so we're reducing it from a positive oxidation state to an oxidation state of 0, and to do that we need to use a reducing agent. Depending on the metal, we use different reducing agents for different reasons. In general, we want to try and use the cheapest reducing agent we can, and in some of the metals you're going to see here, we use carbon. So this first one I'm going to show you is the reduction of, or the extraction of iron. So here's a picture of the iron ore, iron oxide, and here's a picture of elemental iron. I'm going to show you how we convert them. So iron oxide has the equation Fe2O3, and we use carbon in order to extract this, but the reaction that occurs is kind of the reduction of iron oxide with carbon in kind of a roundabout way. So in the blast furnace where this takes place, carbon reacts with oxygen first to create carbon dioxide, and then carbon dioxide will react with more carbon, and this produces carbon monoxide, and this happens at high temperatures. What then happens is that the carbon monoxide is what reduces the iron in the iron oxide. So we have iron oxide react with carbon monoxide, and that will make your elemental iron plus carbon dioxide. In order for this to happen, we need to have 3 carbon oxides in order to, sorry, I've made a mistake there, that should be carbon dioxide. We need 3 carbon monoxides in order to remove each of these oxygens, if you like, to make carbon dioxide. And we also make 2 ions for every iron oxide that we reduce. Copper is the next one we're going to discuss. So copper comes usually as this ore here, which is called malachite, and malachite has the formula CuCO3, so it's copper carbonate. And in order to convert that into copper, the first we've got to do is convert copper carbonate into copper oxide, and to do that all we do is heat it, and that will turn into copper oxide and carbon dioxide. We can then reduce this copper oxide by using just straight carbon. So if we react copper oxide with just carbon, what we'll create is the copper plus carbon dioxide. And to do that, and to balance that, we need 2 of these and 2 of these, so that is how you extract copper. So our reducing agent here is just carbon, and the reason we use that is because it's cheap. So manganese is a very similar story. So this is manganese dioxide, it's ore, and this is manganese metal. So we've got manganese dioxide, and we can use either carbon or carbon monoxide in order to extract this. So if we react with carbon, we'll make manganese and carbon dioxide. And if we react it with carbon monoxide, we'll make manganese and carbon dioxide as well. But with this time we need 2 carbon oxides in order to do this. So manganese oxide can be converted into manganese by using the reducing agent of carbon or of carbon monoxide. Either of those will work. And now we're going to move on to tungsten, which is slightly more complicated than the ones we've just looked at. The reason is that we can't use carbon in order to extract tungsten from its ore. The reason is because tungsten carbide is formed. If you use carbon as the reducing agent. And the reason why this is bad is that tungsten carbide is very brittle. Which obviously isn't useful in terms of its uses in the real world. So instead to extract tungsten from its ore, we have to use hydrogen. So the symbol equation for this is tungsten oxide, which is WO3, reacts with hydrogen, and that will make your tungsten by itself plus water. And to balance that, we can put 3's in front of the water and the hydrogen. The one risk with this is that hydrogen is explosive. So we would prefer to use carbon to extract things from their ores, but if we can't, then we've got to use different elements as the reducing agent. So here, hydrogen is our reducing agent, but the risk with using hydrogen is that hydrogen is explosive, but we have to work with that risk, because hydrogen is the only thing we can use really in order to extract tungsten from its ore. So the next one we're going to discuss is titanium. So titanium ore is titanium oxide, TiO2, and that can be converted into titanium, but again we can't use carbon. It would be nice if we could use carbon, but again titanium carbide is formed, which is brittle, so a similar story to the tungsten. So instead we've got to use a two-step process in order to extract the titanium from its ore. The first step is to convert the titanium oxide into titanium chloride, because then we can reduce the titanium chloride instead. So we react titanium oxide with carbon, which I said would produce carbides, but it doesn't if you also include chlorine in the reaction. So we have titanium oxide plus carbon plus chlorine, and that creates our titanium chloride plus carbon monoxide. We can then use the titanium chloride and react that with either sodium or react it with magnesium. And what this will produce is our titanium by itself, and also either sodium chloride, which is a very stable compound, or magnesium chloride, which is also very stable. Now it's important that you remember or learn the symbol equations for sodium chloride and magnesium chloride. It's a common mistake to miss out this 2 for magnesium chloride, and that will affect the balancing of these equations. So for this second equation, you just need 2's in front of the magnesium and magnesium chloride. For this first equation, you need 4's in front of the sodium and the sodium chloride. So here, the reducing agent is either sodium or magnesium. This first equation is simply converting the titanium from titanium oxide to titanium chloride. There's no reduction or oxidation happening here. Titanium has a +4 oxidation state in titanium oxide and a +4 oxidation state in titanium chloride. So this is just to prepare the ore in order for the titanium to be reduced in these second steps. So now we come to aluminium, which again can't be extracted using carbon, and the reason for this is because aluminium is more reactive than carbon. And so therefore can't be reduced by it, because aluminium will keep hold of the oxygen that it has in its ore. Carbon isn't reactive enough in order to grab that from it, if you like. So instead we have to use electrolysis. So in the electrolysis of aluminium oxide, which is ore, so this is aluminium oxide here, or bauxite is sometimes referred to, and here is aluminium, which we're going to convert it into. We have an anode and a cathode. The cathode is negatively charged, the anode is positively charged, and we have aluminium oxide in here as a liquid, which is Al2O3. Now at the anode, we get the oxygen travelling towards there, because the oxygen is negatively charged, so it's attracted to the positively charged anode, and we get its following reaction. So 3O2 minus makes oxygen plus 6 electrons, and on the other side we get our aluminium attracted to the cathode. So here we have 2 Al3 plus 6 electrons and that makes aluminium. Now both of these you could, if you were writing these just as by themselves, you could double this up, or you could halve this, but the reason I've written them like this is so you can see that the 6 electrons are made here and used here, and so the circuit is formed, and so electricity can flow. But this is how aluminium is extracted from its ore. So some ores don't exist as oxides, as you've already seen with copper carbonate, and zinc especially exists as a sulfide. Now, generally we want to convert these into oxides so that they can be extracted, because generally the reducing agents that we use will remove the oxygen by forming a compound of oxygen once it's removed it. So what we have to do here is we basically have to react this with oxygen to form the oxide. So zinc sulfide will react with oxygen, so 1.5 oxygens, in order to make our zinc oxide, which can then be extracted using a reducing agent. But you also make sulfur dioxide, and this is a problem because sulfur dioxide contributes to acid rain. But that can be used to our advantage because we can create an acid from it. So we can use sulfur dioxide and react it with water and react it with oxygen, and that will produce sulfuric acid, which is a product that can be sold. You will recognise this reaction maybe from year 11, and it's called the contact process. So let's have a look at a few past exam questions now. So this first question says, coke is mainly carbon and is a raw material used in the extraction of iron from iron 3 oxide. Write an equation for the formation of carbon monoxide from carbon. Now, because they haven't stated which equation they want, you can either just go with carbon plus oxygen makes carbon monoxide, make sure your equation's always balanced, or in the blast furnace, I told you that you can the carbon monoxide is formed when the carbon dioxide formed reacts with more carbon to make carbon monoxide. So either of these will be fine. And then it says, write an equation for the reduction of iron 3 oxide to iron by carbon monoxide. So first thing, we need to understand what iron 3 oxide and how to work out the formula of that. When you see Roman numerals and brackets, that basically tells you the oxidation state of that the metal. So iron 3 oxide is going to be iron 3 plus with oxygen, which is O2 minus. So you've got to think about how many of each iron you need in order to make a neutral compound. So if you have 2 irons and 3 oxygens, you'll see that 2 irons will have an overall charge of 6 plus, because each one has a 3 plus charge, and 3 oxygens will have an overall charge of 6 minus. So that will give us an overall charge in the compound of 0, so our compound is Fe2O3. So a reduction of iron 3 oxide by carbon monoxide will be Fe2O3 plus carbon monoxide, which is CO, goes to make iron by itself plus carbon dioxide. And again, we need to balance this, so 2 irons, 3 carbon dioxides and 3 carbon monoxides. So his last question says, the Earth's resources of iron 3 oxide are very large and commercial ores have a high iron content. Give one economic and one environmental reason for recycling scrap iron and steel. So to answer this, you've got to think about how iron is actually extracted from its ore, and it's extracted in a blast furnace, which requires a very high amount of energy in order to melt the iron and heat the carbon together. Recycling iron doesn't require much energy, so the economic reason would be that a lower energy consumption when recycling. The environmental reason would be the idea that carbon dioxide is formed when you use a blast furnace, but no carbon dioxide is formed when you recycle, so there'll be less CO2 emissions. So when you're answering questions like this, you need to think about the two methods that are being used and use a bit of common sense when answering them. So this next question is, pure titanium is extracted by the reduction of titanium 4 chloride, but not by the direct reduction of titanium 4 oxide using carbon. Write an equation for the conversion of titanium 4 oxide and titanium 4 chloride. So you need to know these equations. So titanium oxide is TiO2, and you react that with carbon and chlorine, and you make titanium chloride plus carbon monoxide. And to balance this, you need 2 carbon monoxides, 2 carbons, and 2 chlorines. Then it says write an equation for the extraction of titanium from titanium 4 chloride. So you're going to start with titanium chloride, and you can react with either sodium or magnesium. I'm going to choose sodium, and you're going to make titanium by itself and sodium chloride. And to balance this, you need 4 of each. Remember, you could use magnesium here and make magnesium chloride as MgCl2, and to balance you need 2 and 2 of those. So either of those equations are fine. And then state why titanium is not directly extracted using carbon, and that's because brittle titanium carbide is made. To get the marks there, you could just say the product is brittle if you can't remember what the product is called. Or you can say that a carbide is produced, and they'll assume that you know that that is a bad thing. But that is the most full answer you can give, if you like. So this next question says, aluminium oxide is extracted by electrolysis of molten mixture containing aluminium oxide. State why electrolysis needs to be of a molten mixture. So if it was a solid, the aluminium oxide would not be able to be split because the ions would not be able to move. The ions need to be able to move for them to be able to go to their respective electrodes. So the answer here is ions can move when molten. Then it says write an equation for the reaction of oxide ions to the positive electrode during electrolysis. So oxide ions are O2 minus ions, and they turn into oxygen, but you've got to balance this, so you need 2 oxide ions, and then you also make 4 electrons on this side. Then it says state why the positive electrodes need frequent replacement. Well, I didn't actually discuss that during the slide on this, but basically the electrodes are made of carbon. When oxygen is made at the carbon electrode, because of the high temperatures, the oxygen then starts reacting with the carbon electrodes, and therefore the carbon electrodes start disintegrating, if you like. They're not there anymore, and so they need replacing. So to answer this, you could put carbon electrodes react with oxygen formed there. And then finally we've got give the major reason why it is less expensive to recycle aluminium than to extract it from aluminium oxide by electrolysis. And the reason for this is basically the high energy consumption needed, or high energy needed when you're doing electrolysis, because you need to use a molten mixture of aluminium oxide, which requires a very high temperature. So the major reason why it is less expensive is because there's a lower energy consumption when recycling. This next question is quite common, and it's not specific for this reaction, but basically look at its reactions. I state the role of sodium in this reaction. So the sodium is a reducing agent. So whenever it asks you for the role of something in an extraction of metal question, generally it's going to be a reducing agent, because it's reducing the metal from a positive oxidation state to a 0 oxidation state. This final question. Metals are usually extracted from oxides. Some of these oxides occur naturally, other oxides are made by roasting sulfide ores in air, producing sulfur dioxide as a byproduct. For the extraction of some metals, the oxide needs to be converted into a chloride. The ore molybdenite contains molybdenum disulfide. The first stage in the extraction of molybdenum is to roast the ore in air to form molybdenum oxide and sulfur dioxide. So they've given you all the information you need to write the equation for this. So you've got molybdenum sulfide, roasting in air, so you're adding oxygen, and that makes your MoO3. It's very important that your little o's and capital O's are distinguishable here, and you also make sulfur dioxide, and then you've got to balance this. So you're going to have 2 sulfur dioxides, and then you've got 5 oxygens on the right hand side. So you need 5 oxygens on this side, so it's going to be 5 over 2 oxygens. Then it says the release of sulfur dioxide into the atmosphere causes environmental problems and wastes a valuable resource. Identify one environmental problem, identify one use for the sulfur dioxide. So the environmental problem is that it causes acid rain. And the use for sulfur dioxide is to make sulfuric acid. And it's important that you say that you're making it. If you just write sulfuric acid, that won't get you the mark. You need to make sure that the idea that you're converting the sulfur dioxide into sulfuric acid is there. So using the word make sulfuric acid will be appropriate for that. And then pure molybdenum is formed in the second stage by reduction of MnO3 using hydrogen right equations reaction. Now, you won't have learned this, but it's essentially the same as the tungsten reaction. And if they use a metal that you're not supposed to have learned, that isn't in the spec, then they'll give you as much information as you need in order to write the equation just from your knowledge. So here you've got MnO3 plus hydrogen, which will make your MO and also water. Then you've just got to balance this, putting the 3's in front of the hydrogen and the water. Then finally, state one risk in using hydrogen gas in metal extractions. H2 is explosive.